All right, when I left off, I was going to go over the second example on page 4 of the notes for you. So as we read this one of the things that can be really confusing is the wording on it. Now, from the original problem, I actually did give a little bit of input here on spending less time on chores as being that efficiency is up. So as we read this one, we could become confused. Now we are talking about the average of 16 hours, so again we're talking about MUs, and efficiency being up means that you spend less time on chores. So in the past 16 hours are spent on chores, and less time is the alternative hypothesis, the claim there. And therefore the null hypothesis will be its complement greater than or equal to. And remember that again, if you just put equality in the null hypothesis, that is perfectly acceptable. Now moving on down to our tail of our test, if we go and we look at the inequality for the alternative, our claim, we'll see that this leads us down to being a one-tail test. It's a left-tail test. Now this question doesn't specify an alpha, so just so that we'll have something later on, I'm going to specify right here, let's make it a 1% or 0.1 alpha, a 10% alpha. And that would lead us to our critical value in what we call a traditional test, and it will also help us out in some other types of tests as well. Now a type 1 error here would be that we have said that the efficiency is up when the workers are actually taking longer than that 16 hours. Now again, remember, the type 1 error is the more serious error, and that's why we control it with our alpha. Remember, alpha is the probability of a type 1 error. So we've said that efficiency's up. We're going to praise our workers, maybe give them bonuses. That efficiency wasn't up. They're taking longer. So that's a bad thing for the company here, for this nursing home, if they praise their workers when their workers really aren't doing anything. They're losing money by them being less efficient, but yet then they're praising them. So that's really a lose-lose situation. Now, type 2 error, we've said that the efficiency isn't up when it actually is. Well, that's not so good either, right? Because what we've basically said is you guys need to work harder, work faster, be more efficient when they actually are. That's not very good for morale. Okay, so our decisions here, we've now put this in as a 10% alpha, so 0.1 alpha, which is 10%, which makes it a 90% confidence level. Remember, it's 1 minus alpha percent for our confidence. So if our alpha is 0.1, this is 0.9, and that's a 90% confidence level. So at the 90% confidence level, there is enough evidence to support the claim that the efficiency is up. And then I put in parentheses the workers are spending less than 16 hours on chores, because that's really how the claim was written, that efficiency was up, that we should actually put that into our statement. And the numbers, see, do play a big part in the actual problem, so that's why I put those in there as well. Now the decision of fail to reject at the, and this time I've used significance level, so I'll put in a 10% significance level. There is not enough evidence to support the claim that workers are spending less than 10 hours on chores, and this time I put in parentheses the actual claim that efficiency is up, showing you that although you don't have to use the wording of the original claim, it is actually a preferable thing that we do. Okay, our last discussion is on the critical values. Now, one of the things, or excuse me, not the critical values, the test statistics. And one of the things that I want to make sure you understand about the test statistics is that test statistics for C's or T's, any symmetric interval, they're all going to look the same. Now those for variances, they're going to be a little bit different because they're based upon our chi-square distribution. But if you remember what the chi-squares look like for confidence intervals, you're going to see a relationship here, because the relationship relates back to these standardized values, if you will. So every single test statistic is going to revolve around three basic things. One, the sample statistic that is estimating the population parameter, and the standard error for that population parameters distribution. And then, of course, the distribution is the distribution of the sample statistic. So for population proportions, we have the p hat here. That is the sample statistic that is telling us about our population parameter p. And the population parameter p is going to have a standard error of the square root of pq times the divided by the square root of n. So p hat sampling distribution is a normal distribution with this standard error here. So we're going to standardize the p hats by taking away the p naught, which is the proportion under the null hypothesis, and divide by the standard error. Now, population means when we have the standard deviation known versus unknown, the distribution of the x-bars change. If we don't know sigma, then the distribution for the x-bars is a t. If we do know sigma, the x-bars distribution is a z. And remember that we either have to have an n greater than 30, or we have to have an n that is, or we have to know from the get-go that the standard deviation is an actual known value. If we don't know that, or as actually as normal distribution, so the x's, the values that we're using, those have to be known to be normally distributed if you don't know n is greater than 30. And that's just the kickoff point for the central limit theorem working for us. And again, you're going to notice sample statistic minus population parameter divided by standard error. The only difference between a z and a t is our standard error. Our standard error for a t, standard deviation of the sample divided by the square root of n, versus the standard deviation of the population divided by the square root of n for a z. Now for the chi-squared, it looks different. It's not a symmetric interval, so it doesn't follow this for this test statistic, but this should look really familiar from the confidence interval. Degrees of freedom, n minus 1, times the standard deviation of the sample squared divided by the standard deviation of the population squared. Now remember that these naughts in every single one of these cases, that's what's in your null hypothesis for your hypothesis test. That's where they come from. Now, in the traditional test versus a p-value test, this is what we're looking at. In a traditional test, we're going to hold up our test statistic and compare it to the critical value. And in a p-value test, we're going to say the probability of a value being greater than if it's a right-tail test, less than if it's a one-tail test or a lower-tail test. That probability versus the alpha. That's how we're going to compare it. Now the two-tail's a little bit more complicated. You can put it in one of two ways, and the way that I put it in my notes is the probability of the z or the t being, or the chi-squared, being greater than your test statistic if it's a positive value, less than the test statistic if it's a negative value, and looking at the alpha over 2. The way all computers and calculators look at that is we take twice the probability of z being greater or z being less, or and then we compare that to alpha. It's just easier to be consistent that way, so you're always making the comparison to alpha. So now what we're going to do is we're going to get into testing these claims about proportions. So we'll just be doing some examples for proportions in this particular one. And then the next section will be about means, and so on and so forth. And that's how the rest of the chapter progresses through here. And I believe that the notes there may be off because it says section 7.3, and I think it's actually 8.3, so forgive that little error there. Alright, now I think that rather than continue on with this video and start in on the proportions, I'm just going to start a new video because I don't want to run out of time when I'm right in the middle of an example. I rather have the entire example one video. So I'll see you in the next video.